And now we will welcome our second speaker for this session, Andrés Gómez Tato from CESGA, who will, after the algorithm enablement from Jeannette, will give a perspective more from the infrastructure side. Andrés is the head of the Applications and Project Department at the Galician Supercomputing Center, and basically is the head of quantum technologies at CESGA as well. Thank you very much.
Thank you very much. Thank you very much for inviting me to be here after the fantastic presentation from Jeannette. My work is easier, in fact. I will try to provide you a brief vision about how to integrate HPC system with quantum computers and the work that we have to do, take into account the requirements of the users at the different levels. Just if you don't know us, we are one of the older supercomputing centers in Spain. In fact, we are in the northwest of Spain, in Santiago de Compostela. Maybe you know the city. And we integrated our first quantum computer in 2023. It was a challenge to install the system in the same computer room, but it was also a challenge to integrate the system with the HPC system. I will describe later the infrastructure that we built to make this experience. Just to announce, we have been awarded with the AI factory devoted to One Health concept. That is our next great project. Some important remarks about quantum computing, because it's important to know exactly where we are at this moment. There are many different technologies. We have superconducting, we have qubits, we have ions, we have photons, we have many different technologies, and the winner is not clear at this moment. So it's very difficult to define standards to access the different technologies because the operations that they can do are completely different. Secondly, they are basically analog devices, and we want to operate with the system using digital operations. And this is complex. In fact, for the reason we have the fidelity parameters that are there in order to understand which is the performance, the single performance of the qubits. Third point is that all algorithm is hybrid. We don't have any single algorithm that run only in quantum. We need at least pre-processing and post-processing, because the only thing that we understand is classical information. This is important. For example, the famous OR algorithm has several steps, but only one is quantum accelerated. The rest are pure classical algorithms. We understand in the HPC community that quantum processing units are basically accelerators. Jeannette said before that in a full program, we have classical, and quantum is basically a subroutine, a small kernel, in a full workflow. That this means that we have to integrate the system. And finally, QPUs are still on motor. We have basically prototypes, but we want to extract information from them. And in fact, we are waiting for the next generation that is full fault-tolerant quantum computers. But in the meantime, we have to work with the technologies that we had at this moment. So how to deploy a quantum computer, a quantum unit, in a quantum center, or in a supercomputer center, in my case? Well, we have three main models. The first one that was maybe the dominant one during many years is a standalone system. Maybe you have been working with one of them through cloud environments, or this kind of very nice interfaces that we have in cloud. But it's an old way to use these quantum computers. The next step is integrating the quantum units with the HPC using typical links as cables, as Ethernet, but without very tight integration. In fact, in some cases, we are integrating HPC with remote systems that are allocated on demand for the work that we have in HPC. And finally, for the future, We expect to have the quantum processing units integrated, tightly integrated with the CPUs and other accelerators and GPUs in order to extract the better performance of all the systems. From the user's perspective, there are three main levels of knowledge. First of all, the users that want to use the quantum computers at high level, like any programmer in the classical area at this moment. There are a second level that are a medium level optimized programmer that they want to access their system to know the system better, and they want to extract the maximum performance, knowing exactly what kind of operations can be executed in each platform. And finally, we have people that work at low level. At low level, in many cases, is to work with pulses, with the analog signals that we have to send to the qubits. If we see the kind of jobs that we are receiving, first of all, that is interesting, I will explain later, we can understand the quantum computing as a quantum lab directly. They are quantum devices. But of course, the main part is the research or proof of concept. We want to know if the quantum computer can be used to some workload. Jan presented some of them before. And for example, in Quantum Spain, we received 53 proposals that have been selected to use the quantum computers with more than 150 users that more or less fit in this profile. But of course, we have people that just want to test the quantum computer. In this case, they submit a very short jobs, very low number of jobs. And, but we have also integrators, developers of tools in this software stack that Annette presented before that need sometimes short access, sometimes very long access. And finally, that is important because we have a shortage in the skill of the people. We need training, the possibility of accessing to this system for training, just for training. And for example, we organize every year one thing that is the International Quantum Masterclass in order to provide students from the university, but also from the secondary schools access to these computers. That is a challenge because we have to support hundreds of users simultaneously in our computer. This year, we were 180 people submitting jobs during less than 1 hour, and we have to return the results faster, very, very fast, because they don't want to wait for a result for a very small circuit. It was a challenge. Because I'm in Germany, and we are in Germany, one proof of concept that we are executing is how to improve the beer in order to select molecules for improve the freshness of the beer. This is a nice collaboration project with the company, with the manufacturer of the beer, with Fujitsu and one university, and we are comparing the menthol molecule with other that are in the market in order to see if these molecules can interact with the protein that generate the freshness in our body. It's an optimization problem, basically, using quantum. I have to say the results are promising. It was a very limited example without benefits at this moment, but we hope that in the future we will have benefits using quantum computers. But one important thing, this was executed in a real quantum computer, not in simulation. I told before that one of the main use or typical use of our quantum computer is to use the quantum computer as a lab. This is a very nice example. This is a reproduction of a very famous experiment in physics that is from Alan Aspect, a French physicist, that demonstrated that the quantum is real, basically. And we can run now in a quantum computer in only a few minutes if you have expertise in how to program these quantum computers. Alan Aspect needed 7 years. Okay? This is the difference. Now the students can work with real quantum devices. Of course, as I said before, quantum computers are analog, so you have to calibrate the information, and you have to calibrate how to interact with the quantum computers. This is an example of a typical calibration where we need to find the frequency to interact with one qubit. This is a very easy example that you can execute in 5 minutes in order to find this frequency. Of course, the problem is when you have these kind of things. Oh, what's happening? Which is the second peak that I have there, or which are the symmetric peaks that are in there? Okay, I can explain that using physics. In fact, I needed a couple of days to find the reason of the second peak and more time to explain the other 2 peaks that I have in the video. But it's something that press the physicists to learn what's happening with the systems that we have there. And of course, you can do experiments. But for course, the typical use is using the quantum computer as a digital computer. Don't try to understand that if you have not programmed before in quantum computer, okay? But any box there, a square box, is an operation, a digital operation that we try to execute in a qubit. A qubit is this line, and the name of this is typically a circuit, okay? But there is one very nice algorithm that is the iterative quantum phase estimation. In this case, you can break the top algorithm in several steps that you can submit, measure the result, use the result to generate the next circuit, and again to submit the next circuit, and using an iterative process. Here, the latency for executing this algorithm is very important. So this is a typical problem in HPC. We need to address we need to address this kind of demand from our users in the future. Typically, in the current infrastructure, we are using parametric quantum circuits. Before, Janet explained some of them, but this is a very nice picture to understand what's happening in a variational quantum computer solver. It is an algorithm to calculate the low energy of a quantum system. But the most important part is in the left, in the QPU. We have to execute per step several circuits, several subprograms in order to calculate the expectation value of the energy of the molecule, for example. Okay? This means that we have to execute maybe tens or maybe millions of circuits, in some cases during the optimization, because some molecules need thousands of different calculations, different terms of the Hamiltonian that we have. Again, depending on the algorithm that you are using for making this classical optimization, this loop, maybe you need a very large number of executions. This means that we need a very high throughput, a very low latency. These are requirements that are there. So, what is the solution? For an infrastructure, we need benchmarks. Benchmarks to understand what's happening with the systems, benchmarks to understand what's happening with the QPUs. And we are in the house of top 100, so we can remember that in the case of classical benchmarking, we have clear benchmarks with clear rules to understand which are the performance of the different systems, the performance of different elements that are there in the market. We need something similar in the case of benchmarking. We have a full stack, so we need to define benchmarks that test the different parts of the software stack and the hardware stack. And sometimes it's very difficult to put the line between what is a QPU and what is a classical element. In fact, I had strong discussions with one of the vendors to define what exactly is a QPU for them. And sometimes they exclude the classical electronic that manipulate the qubits. In my opinion, it's wrong to do that. Okay? But of course, we started making an initial benchmarking at the application level. As Janet said, we have kernels, and our idea was exactly the same that we had in the classical part. We need to extract the kernels of the applications and define a clear benchmark using this kernel. But we need reproducibility. This means if I execute the benchmark 2 times, I need to have the same result, or at least the same result with the statistical confidence. We need something agnostic because we need a benchmark to go to all the layers and measure the different capabilities of the layers. Okay. But the most important part, we need to verify, in this case, the solution. This is something that is not usual in the classical part. Of course, we have benchmarks that verify that the solution is correct, but only verify the solution. Here it's important to know if we generate the correct solution, and that we can find a metric about the distance between the real solution and the produced solution that we have. And for this reason, we need something that can be classically calculated and very easy calculated. For example, in one of the cases is the integral of the sin function between two values that is very easy to calculate even by hand, but it's very difficult to calculate using a quantum computer. But this is only one part. In the layers of Janet presented before, we can see several components. And we are now starting to think about the integration between classical computers and quantum computers. For this reason, I need to introduce my platform, because it's very difficult to explain why we need these kind of things. Well, Kumio, not Kimio, Kumio, because it's in Galician, my own language, is an infrastructure that was designed for quantum information research. It includes one QPU integrated with an HPC system, integrated with an emulator, and integrated with an storage system. So this is a small HPC center of the future, okay? The problem is the price. It was very expensive. But the problem is how to use this system, how to integrate the solution taking into account that we have users that want to execute very short circuits and others that want to execute large problems that need hours to solve. So we had to define a full infrastructure, a full system that is divided in two parts. In the yellow one is the usual use of an HPC system where a user submits a job that needs maybe hours of using the QPU and interfacing with the QPU. In our case, the QPU is connected to a single node, a single classical node in the HPC, like a GPU is connected to a single node in a HPC environment. The connection is through Ethernet at this moment, because we don't have any possibility yet with the vendor, but it's the typical use of an HPC center. But at the same time, we wanted to provide services to others in order to have this access, fast access in some cases. In this case, we created a proxy that is submitted to the same queue, is waiting there to have access and open a socket during just a couple of minutes in order to execute these small jobs. The software stack is complex, is very easy at the end. Basically, it's composed of the programming languages and some stack to make the communication between the classical node and the quantum unit, but our idea is to reduce the latency, to increase the speed of this connection. For this reason, we use a zero message queue server and client in order to transmit information between them. Of course, in the QPU side, we have to process the information. We send the classical or the circuit information that is received in several interfaces, and we have to make converting this information to the final representation. We have to the final representation convert into pulses. These pulses must go to the FPGAs, execute, and back the information to the system. Everything is there inside the QPU, and for me, it's part of the QPU, and it's software. So we need to test the software. As Janet said before, the quantum computers are slow, but we need to speed up at maximum the velocity of execution. This is a very simple example When you can see that in our case, we can submit a circuit in less than half second and start to make the process. We have a flat area that is due to the processing of the input, and later we have an increased return time due to the execution of the different shots. This means the repetition of the circuit that we need. And we have two areas there that are related with the buffering between the FPGAs and the classical node that is connected to the FPGAs. This is the kind of information that we extract classically, but we want to extract this information in the QPUs as well. This is our in progress. We will improve the system and the definition of disbursement, and we will provide this information, and we will try to run in different platforms in order to understand the problems. Of course, we have to also understand the parsing between the intermediate representations that you're using, OpenQuasar 2, OpenQuasar 3, quantum intermediate representation, and the real execution. You can see that we have very big differences depending on the parser. So we have to improve the parser, and we have to improve all the parsers and all the methods that we have inside the QPU, because we have more than 3 orders of magnitude between the time that I need to execute the circuit and the time that I need to process the input for executing the circuit. So we have a lot of capabilities there to improve the performance of the QPUs. Well, which is the future? Well, the future, from the point of view of an HPC center, is to have several QPUs connected to several nodes in order to make parallel applications. But we need, initially we can do that now, but without the quantum communications. That is a technology that is under development at this moment. Maybe at the end of this decade, we will have some initial prototypes. But clearly, before we can use this technology for running some initial experience, but we need to understand how to manage this infrastructure, how to execute workflows in this infrastructure. So for this reason, we are developing an emulator of a distributed quantum infrastructure to run on HPC. The idea is to have virtual QPUs, and when we have physical QPUs, you can link as well the physical QPUs, and to understand how to manage applications, to understand how to manage the different noise profiles that we can have in the different QPUs, or even the capabilities, the schedulers, how to make a quantum program parallel. There are many different techniques that as a software developer can develop using this kind of infrastructure. In fact, we are working with 2 companies. One of them is a local company from Galicia that is developing a Rust environment for using this infrastructure. And you can see that they can run in different QPUs. Depending on the number of qubits, they can have a very large gain in returning time that is important from HPC. And we were working also with a British company, the name is Quoro, that is developing a similar product. And in this case, they are trying to making real speed up with the real hardware that we have, but to test the software, sometimes use our own platform, Kunga, in order to make initial tests. Finally, I have to say that we cannot do that without support of the public administrations. It's very expensive to have an infrastructure. In fact, the test that I showed you had a cost around 6,000 euros in our own platform. If you execute in a cloud environment, maybe you need 3, 4, 5, or 1 million more budget in order to run the test. So my gratitude to them, and also to my team, my research team at the university that collaborate with us. And that's all. Thank you very much.
Thank you, Andrés. So we have now a couple of minutes to take some questions. Maybe, well, I have one here. So what open source projects are you seeing as most useful in the QPU HPC workflow? And what do you wish would be developed or released as open source?
Which is the most one at this moment? Well, it's very difficult to say. There are many candidates to explore the interface between HPC and quantum computing. There are new algorithms in the market. Every day we have more there, but it's very difficult for me to define a winner at this moment. Okay? The same like in the hardware level. In the hardware level, we have many different technologies. Which is the winner? I don't know yet. But I have seen a clear change during the last 3 years, more or less, where we have more complex hybrid algorithms between the classical part and the quantum part. In fact, there were very nice presentations during this conference about this possibility, using the QPU to generate data that finally is used in the classical part in order to find the final values, the final values of a molecule, for example. But for me, it's very difficult to say that. And the second part was?
The second part was, what do you wish would be developed or released as open source?
In this moment, I think that we must release everything in open source, because we are working in prototypes. We are working with something that we must learn from others at this moment in order to help them to improve or to open the solutions to others that can provide us with new knowledge or with new capabilities. For this reason, we release everything as open source at this moment.
Thank you very much.
You're welcome.
Do you have other questions? Okay, then I think with that we can close the session. Thank you very much, Andrés. And thank you all for attending, and I hope that these two presentations provided insights on the tools that are being developed to help foster adoption on these hybrid schemes. Thank you very much.
You're welcome.